Today I'm going to be talking about mathematical induction, how it works, and how we can use mathematical induction to prove certain statements. So mathematical induction has three main steps to it. You show that the statement is true when n equals 1. You assume the statement is true when n equals k. And then you show that the statement is true when n equals k plus 1. And the reason that this works is it's like dominoes. You've shown it's true for when n equals 1. And then you've shown that if it's true for n equals k, it's also true for n equals k plus 1. And keep in mind that this only works with integers. So what we've done basically here is we've shown it for 1. And if k equals 1, so we can let k be 1, we've shown that the statement is true for 2. Then we can let the statement be k, then we can let k equal 2. And we've shown that when it's true when n equals k plus 1, which is showing it for 3. And then we can let k equal 3, and then we've shown it for k plus 1, which is 4. And then you get 5, 6, 7, 8, and so on and so forth. So that's basically how it works. And this is very useful when we're trying to prove statements for integers. So we have this problem here. We want to prove that 3 to the power of n minus 1 is a multiple of 2 for all positive integers n. And we can prove this using mathematical induction. So the first step 1, is to show that the statement is true when n equals 1. So when n equals 1, we get 3 to the power of 1 minus 1, which equals 3 minus 1, which equals 2. And we know that 2 is a multiple of 2, right? Because 2 times 1 is 2. So we've shown that it's true when n equals 1. Now, we want to assume the statement is true when n equals k, and then use that fact to prove that the statement is true when n equals k plus 1. So we get step 2 here. So when n equals k, we get 3 to the k minus 1, right? And we're just assuming it's a multiple of 2. So we can write 3 to the k minus 1 is a multiple of 2. And keep in mind this is an assumption. And we're going to use this, we're going to treat this as a fact, and we're going to use this to prove that it's true prove that the statement is true when n equals k plus 1. So we have step 3. When n equals k plus 1, right, we plug in k plus 1 for n, so we get 3 to the power of k plus 1 minus 1. And we have to manipulate this in a way that we can show it's a multiple of 2. So this equals 3 times 3 to the k minus 1. And we can split up 3 into 2 and 1, 2 plus 1, so we get here 2 plus 1 times 3 to the k minus 1. And now we just distribute, we just multiply and we distribute, and we get 2 times 3k, right, plus 3k minus 1. And this is a multiple of 2, because what we have here is 2 times something, which is 2 times something will always be a multiple of 2. And what we have here is another multiple of 2. And this part, the reason this is a multiple of 2 is because of here. We assume that this is true, right? So we have a multiple of 2 plus a multiple of 2. And that will give us a multiple of 2. So 3 to the power of k plus 1 minus 1 is a multiple of 2. And this is it. We've proven that this is true for all positive integers n. Because what we have is we've shown it's true for 1, which is the first positive integer. And if it's true for n equals k, it's true for k plus 1. So if you let 1 equal to k, we've shown that it's true for 2, because k plus 1 is 2. And then if you let k equal to 2, we've shown it's true for 2 plus 1, which is 3. And then we've shown it's true for 4 and 5 and 6 and 7 and so on and so forth. So this is how we've proved the statement is true for all positive integers n. So now we have this problem over here. We want to prove that n cubed plus 2n is a multiple of 3 for all integers n. And this one's slightly different from the previous problem because now we want to prove it for all integers n, not just positive integers. So step 1 is the same. So step 1, when n equals 1, we need to show that the statement is true. So when n equals 1, we have 1 cubed plus 2 times 1, which equals 1 plus 2, which equals 3. And we know that 3 is a multiple of 3. Step 2 is also the same. So we have I just need to get my pen. So we have step 2. We're going to assume that the statement is true when n equals k. So when n equals k, we have k cubed plus 2k is a multiple of 3. And this is an assumption. So we're not proving this, we're just taking it to be fact. Now, step 3 is where it's slightly different. So for step 3, the starting is the same. We want to use the step 2 to show that when n equals k plus 1, the statement is true. So when n equals k plus 1, we have k plus 1 whole cube plus 2 times k plus 1. This will give us k cubed plus 3k squared plus 3k plus 1 plus 2k plus 2. Rearranging these terms, we get k cubed plus 2k plus 3k squared plus 3k plus 3. I got this plus 3, I added the 1 and the 2. So this equals k cubed plus 2k plus 3 times, we're factoring now, 3 times k squared plus k plus 1. We were factoring this side over here. Now this is a multiple of 3 because from step 2 we have that this is a multiple of 3. So we know this to be a multiple of 3. And this is 3 times something, and 3 times something is also a multiple of 3. A multiple of 3 plus multiple of 3 is a multiple of 3. Well, we're not done here. What we've done so far is we've proved the statement for all positive integers. We've proved it for 1 and everything above 1, k plus 1. So to prove it for everything below 1, because we are trying to prove for all integers, not just positive integers, we need to prove that the statement is true when n equals k minus 1. Because from k plus 1, you get 1, 2, 3, 4, 5, all the way to infinity and beyond. And for k minus 1, you're going to get the 0, negative 1, negative 2, negative 3. So we need to show that the statement is true for k when n equals k minus 1. So when n equals k minus 1, we have k minus 1 whole cube plus 2 times k minus 1. Expanding, we get k cubed minus 3k squared plus 3k minus 1 plus 2k minus 2. And rearranging just like we did in the when we were proving it for k plus 1, we get k cubed plus 2k minus 3k squared plus 3k minus 3. And what we have here is k cubed plus 2k, right? Minus 3k squared minus k plus 1. And this, again, this part is a multiple of 2 and we assume that. And this part is again a multiple of 3 because 3 times something is a multiple of 3. and a multiple of 3 minus a multiple of 3 is also a multiple of 3. So when we've done this, now we've proved the statement for all integers n. Here we have a different type of problem. We want to prove that the sum 1 plus 3 plus 5 plus all the way till 2n minus 1 equals n squared for all positive integers n. And we use the same steps. So we have step 1, we're showing it's true when n equals 1. On the left hand side we just have 1, and this has to equal 1 squared, and 1 squared equals 1, so it's true. Now step 2, right, we're assuming that it's true when n equals k. 2. So when n equals k, we have the sum here, 1 plus 3 plus 5 plus ... all the way till 2k minus 1 equals k squared. This is an assumption, and we'll treat this as a fact to prove the statement for when n equals k plus 1. So we have here, when n equals k plus 1, step 3, when n equals k plus 1, the series is 1 plus 3 plus 5 plus ... all the way till plus 2 times k plus 1 minus 1 equals k plus 1 squared. And we have to show that this is true using this fact, using the step 2 fact. So let me just simplify the left hand side a little bit. So 1 plus 3 plus 5 plus ... plus 2k plus 2 minus 1 is just plus 1 equals k plus 1 whole squared. Now this is an arithmetic series, right? And this is the k plus 1th term, right? K plus 1th. So the term before the k plus 1th term is the kth term, and the kth term is 2k minus 1. So the left hand side is this is the same thing as saying that 1 plus 3 plus 5 plus ... plus 2k minus 1 plus 2k plus 1 equals k plus 1 whole squared, because this is the kth term, and this is the k plus 1th, right? And the k plus 1th follows the kth, or the kth term is before the k plus 1th. So now we're going to do some substitution here. This series, this whole part of the left hand side, is equal to k squared, and we know that because we assumed it up here, right? So this whole part, we're just going to substitute k squared into it. So what we have now is k squared plus 2k plus 1 equals k plus 1 whole squared. And let's expand and simplify. Equals k squared plus 2k plus 1. And we have that k squared plus 2k plus 1 equals k squared plus 2k plus 1, which is true no matter what k is. So now we've shown that for if n equals k, the statement is true, then it's true for when n equals k plus 1. So we have now shown the statement is true for all positive integers n. Because again, it works like this. You've shown it's true for 1, and you've shown it's true for all consecutive integers after it.